All right, excellent. We are live for Cheg's live office hour, focusing on trigonometry this hour. We're going to give people a couple moments to come streaming in, and then once they do, we'll go ahead and officially get started. But I'm really excited to see everybody here today. We are here every week at this time to answer your questions with a virtual office hour. So let's see. I think people are starting to stream in, so we'll go ahead and officially begin. So a big hello to everybody. Welcome to our live office hours brought to you by Cheg with Wallace STEM. You might recognize me from my channel at Wallace STEM on TikTok, Instagram, Twitch, all the things. At Wallace STEM, I do memes about calculus. So I say come for the memes, stay for the math. It's a lot of fun. But we are here today to do a live office hour. Some of you have been here before and you know kind of how this works. But for those of you that are here for the first time, the goal here today is to help you understand your trigonometry course and concepts better. I'm here every week to do just that. You can think about this like your virtual office hour. So if you have any questions at all, don't be shy and drop them in the chat. We're going to kick things off with a problem that I've prepared, but I hope that as you're logging in, you tell me what questions you have so that we can go ahead and focus really on your topics. What are you doing in your trigonometry classes right now? Are you doing proofs? Are you doing graphs of sine and cosine? Are you doing application problems? Are you doing polar coordinates? Tell me what you're doing and we'll do a problem based on your question. But I want to start off with a proof because I think those are some of the most challenging things that we see in trigonometry, possibly because it kind of exposes where we might have some gaps in our algebra knowledge. So let's see if we can close those and find some success. Today, we're going to start by proving that 1 plus tangent squared of theta over the tangent squared of theta is equal to the cosecant squared of theta. And with proofs, the general idea is we want to start on one side and manipulate it to look like the other side. So I always suggest you start on the more complicated looking side because it's easier to get simpler than more complex. Obviously here the left side is our more complicated side. So what can we do with this? Well, there's a couple ways we can go about it. One thing you might see is 1 plus tangent squared is one of our trig identities. That 1 plus tangent squared is secant squared. So I'm going to rewrite 1 plus tangent squared as secant squared, and we'll put that over tangent squared of theta. Now, from here, what can we do? If you don't know what to do at any point in a proof, what I generally recommend you do is rewrite everything as sines and cosines. So secant squared as the reciprocal of cosine is 1 over cosine squared. And tangent squared, that's sine squared over cosine squared. Well, whenever we're dividing with two fractions, which is really what we're doing here, to divide with two fractions, what we're going to do is we're going to multiply by its reciprocal. So let's try doing 1 over cosine squared, and we'll multiply by the reciprocal of what's down here, which is cosine squared over sine squared, which happens to be really, really nice because as you can see, cosine squared can reduce out of the top and bottom, leaving just 1 over sine squared of theta. Well, you should recognize 1 over sine squared of theta. Sine squared in the denominator is the same as its reciprocal, which is cosecant squared of theta, which is exactly what we were going for here on the right side. So we'll put our little box to show that the proof is done. Some instructors prefer QED, which is Latin for which was what to be demonstrated. Quid eram demonstratum is the Latin phrase. But that's how I would go about proving this one, using our Pythagorean identity to write this as secant squared, and then writing everything as sines and cosines, and simplifying that resulting expression. So hopefully that was helpful to you. I see lots of questions coming in. We're going to try and really focus our questions on some trig content. We're going to do some algebra content. If you come back in an hour and a half, we've got a live algebra-based pre-calc hour. And in that hour, we can do inductions and we can do some of those other things that are being asked about. But I saw something about wanting to work with proofs with sine of a plus b. So let's try, let's see, the one I prepared is cosine of a plus b. Is that okay? It's a really similar property, but cosine of a plus b over cosine of a minus b, we're going to prove that's equal to 1 minus the tangent of a times the tangent of b over 1 plus the tangent of a times the tangent of b. And let's see if we can do this proof. Now with this proof, we really can start on either side. They're probably just about equally complex. Let's start on the right side though. It just feels like there's more pieces there. So what I'm going to do is I'm going to rewrite these tangents as sines and cosines. So we end up with 1 minus tangent is sine A over cosine A. Tangent B is sine B over cosine B. All over 1 plus tangent A is sine A over cosine A. Tangent B is sine B over cosine B. Now, whenever you change an expression to have all sines and cosines, it's very likely you're going to end up with little fractions inside of a bigger fraction. And so whenever we have a little fraction inside of a bigger fraction, the way we fix it is we're going to multiply by these denominators. We're going to multiply by cosine A, cosine B on top and bottom. And if I do it on top and bottom, it's going to distribute onto both terms, giving us cosine A, cosine B over here as well. But what's nice when I do that is the cosine A's reduce out and the cosine B's reduce out on the right side. So what the resulting expression, what's left, is going to look like a, cosine B, minus sine A, sine B, all over cosine A, cosine B, plus sine A, sine B. And this is where we get to use that property, the sine of A plus B or the cosine of A plus B property, because you might recognize this looks like that key identity for the cosine of A plus B, exactly what we're trying to get to. We call that our, what's the name of that? The sum and difference identity? Yeah, it's the sum and difference identity. So all of this stuff is going to simplify to the cosine of what A plus B is. And the sum and difference identity for cosine, cosine, sine, sine is the cosine of A minus B, which matches exactly what we're looking for on the right side. So we're going to call that done. QED, trig proofs are one of the big things that we see as we're working through our trigonometry class. The other big thing that we see, as Jack on TikTok points out, is the unit circle. So I'm going to erase this. Keep those comments and questions coming in, but let's look at Jack's question about how the heck can we memorize and learn the unit circle quickly. That is such an important skill to be able to do. And I'm assuming you're not just asking about the radians, but also the coordinate points, the root 3's over 2's, the 1/2's, the root 2's over 2's, all of that. So let's look at how I like to remember the unit circle, and hopefully this will be helpful to you as you go through your trig class, because you're going to use this unit circle all the time in your trig class, and you're going to continue to use it as you go on to other classes, such as calculus, differential equations, and some of your engineering and physics classes as well. How I like to start remembering the unit circle is first I'm going to think about this as a clock. So you've got high noon straight up. Then you've got 1 o'clock, 2 o'clock, and 3 o'clock is off to the right. 4 o'clock, 5 o'clock, 6 o'clock's off to the bottom. 7 o'clock, 8 o'clock, 9 o'clock's off to the left. And then we've got 10 o'clock, 11 o'clock, and 12 o'clock again back at the top. What's really nice about this is these are the key points with a denominator of 6. So if I start over here, because we know the unit circle starts off to the right at 0, coming up, we're going to count pi over 6. So we've got 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6. Is that too low? Are we still on the screen? Yeah, we are still on the screen. 10 pi over 6, 11 pi over 6, and 12 pi over 6. Now, as you do that, some of those fractions can be reduced. And so we do want to go through and reduce those. So 2 pi over 6, that one does reduce to pi over 3. 3 pi over 6, that reduces to pi over 2. 4 pi over 6 reduces to 2 pi over 3. 6 pi over 6 reduces to just pi. 8 pi over 6 reduces to 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 reduces to 5 pi over 3. And 12 pi over 6, that reduces to 2 pi. And so by just keeping track of the points on a clock and counting around pi over 6, we've got almost all of the points we need for the unit circle. But one of them's missing. Do you know which one's missing? If you said the pi over 4s, you're exactly right. The pi over 4s are missing. And so to do that, I'm going to split what's left into quarters, marking these quarters all the way around. And those quarters that are in between each of these are every odd pi over 4. So that's 1 pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So I've got a clock for most of them, except for the quarters. Those are at the pi over 4 locations. So that's how I remember that part of the unit circle. The next thing I need to remember, though, is the coordinates on the unit circle. When I'm looking at the coordinates, there's really only 3 options. Well, okay, not quite. There's the obvious ones at the axes, at the top and the left and the bottom and the right. It's a unit circle, so the distance is 1. So this is 1 to the right and no up. So this is at the point 1, 0. This is no to the right and 1 up. So this is at the point 0, 1. 1 to the left, that's -1, 0. 1 down, that's 0, -1. Okay, so those, straightforward. The rest, though, there's only 3 possible values. 1/2, root 2 over 2, and root 3 over 2. They're all over 2. They're 1, 2, 3 over 2. Square root of 1, square root of 2, square root of 3 over 2. Cosine is the x-coordinate, so it's going to start counting down, while sine is going to count up. So the x value is going to go from 4 to 3 to 2. Whoops. I didn't realize I was inside for this point. So 3, 2, 1, and it's going to be the square roots over 2. Square roots over 2. Square root of 3, square root of 2, square root of 1 over 2. The signs are going to count up. So there's 0 here, so we're going to go to 1 over 2, 2 over 2 with the square root, and 3 over 2 with the square root. And then I can use these key points to kind of reflect all over the circle. The other thing I think about too is, like, if I wanted to do 5 pi over 6, instead of counting all the way over there, I see that the x coordinate is long and the y coordinate is short. So the long x coordinate is the bigger root 3 over 2, and the short y coordinate is 1/2. Because it's backwards, this first one's negative, and so the cosine at 5 pi over 6, the x coordinate is negative root 3 over 2, and the y coordinate is 1/2. And on TikTok, Arip, I don't know if I'm saying your name right, brought up a great point that there's a nice little hand trick to remember the unit circle. If you stick your hand here in the first quadrant, it really gives you all the points. So here's 0, 1 pi over 6, 1 pi over 4, 2 pi over 6 or pi over 3, and pi over 2. So if I think about my hand, let me see if I can make it bigger in the, well, let me get this out of the way. Then I'll show you how that hand trick works really nice. That way, because you always have your hand with you on your test, you don't have to write anything on it though, because the hand becomes the first quadrant of the unit circle. So right here, this is 0, and then we're going to count up for sine, down for cosine. So the sine at 0 is 0, then square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, which reduces to 1. Cosine counts up. So it starts with the square root of 4 over 2, and it goes 4, root 3 over 2, root 2 over 2, root 1 over 2, and root 0 over 2. And that's all just right on your hand. So hopefully that can help you also remember that. I've seen another way to remember it too, where people just list the angles out. So you've got pi over 6, pi over 4, pi over 3, and then I guess technically pi over 2, and 0 should be on here as well. And if we look at the cosine and the sine, and even the tangent of the angles, there's a really nice pattern that comes off of this. So for cosine, I mentioned cosine's going to start at the top and count down. So at the top, it's the square root of 4 over 2, the square root of 3 over 2, the square root of 2 over 2, the square root of 1 over 2, and the square root of 0 over 2. All of them are over 2. They're all square roots, and they just count down. Well, the sine is going to count up. So sine starts with the square root of 0 over 2, the square root of 1 over 2, the square root of 2 over 2, the square root of 3 over 2, and the square root of 4 over 2. Now, some of those square roots do simplify, so you want to go ahead and do that as you're making your chart. Square root of 0 is 0, and 0 divided by anything is 0. So that one simplifies to 0, same thing over here. The other one that simplifies nicely is the square root of 1 is just 1, so the square root kind of just goes away. The other one that's nice is the square root of 4 over 2, because the square root of 4 is 2, divided by 2 just gives me 1. So the square root of 4 over 2 reduces to 1. But it's that same general pattern, though. It's always square root over 2. With cosine, it's 4, 3, 2, 1, 0. With sine, it's 0, 1, 2, 3, 4. Just count up and down. Well, what about the tangents? Tangents are always the tricky ones. They get students because we don't spend as much time looking at tangents. So the way tangent works is tangent is sine divided by cosine. Sine divided by cosine. I'm going backwards as I do this. So all I have to do is divide. 0 divided by 1 is 0. And so the tangent of 0 is 0. When I divide these, sine divided by cosine, the over 2's, you can just completely ignore the over 2 and just do 1 over the square root of 3. Here you can do square root of 2 divided by square root of 2, and anything divided by itself is 1. Here you can do square root of 3 divided by 1, and that's just going to be the square root of 3. And 1 divided by 0, we can't divide by 0, so it does not exist. And so in that way, that's another nice way, just making a chart of all the values, and then you can kind of keep track of them and remember them. There are lots of ways to keep track of the unit circle, the chart, the circle, thinking about it like a clock, using the hand trick that we talked about. Whatever you use doesn't really matter as long as you know these values, because knowing these will help you significantly as you go through your course, because you're going to have to solve trig equations. And when you're solving trig equations, you need to know these values. Let's solve a trig equation. And as I write this trig equation that we're going to solve, I want to remind you this is your trigonometry review. So tell me what questions you have from your trig classes. Do you want to see graphing? Do you want to see polar? Do you want to see more proofs? Do you want to see more solving? Tell me what trig concepts you want us to look at. We are here for the entire hour answering your questions. And we're going to do next, let's take a look at sine squared minus cosine squared equals 1 plus cosine. I think that's going to come out doing what I want. Whew. Sorry, you see me scratching my nose a lot. One of my pens has this really potent smell to it, and it's like makes me want to sneeze. It's terrible. All right, but I digress. We'll go on. All right, so with this equation, as we're trying to solve it, it is really challenging to solve equations that have both sine and cosine in the same problem. So it'd be really nice if we could change one of these into the other. Since there's two cosines, let's go with a goal of having all cosines, which means we want to get rid of the sine. And the way we're going to get rid of the sine is we can use the Pythagorean identity. Remember, the Pythagorean identity tells us that sine squared plus cosine squared equals 1. So if sine squared plus cosine squared is 1, subtract cosine squared, and we get 1 minus cosine squared is equal to the sine squared. And then I'll do a minus cosine squared equals 1 plus cosine. Now, whenever we see the variable squared and the variable not squared hanging out in the same problem, we want to set that equal to 0 so that we can factor it. So we have 1 over here. If I subtract it from both sides, we get 0. That's really nice. Whoops. So I'll just go ahead and cross it off, subtracting 1 from both sides. This is cosine squared. Negative cosine squared and negative cosine squared is negative 2 cosine squared. If I add it to the other side, we'll end up with 0 equals 2 cosine squared of x plus a cosine of x. And we can solve this by factoring out a cosine of x, leaving behind 2 cosine x plus 1. Based on this, orange. I knew I was missing a color. Once it's factored, we can set each individual factor equal to 0. So I can set cosine x to 0. And I can set 2 cosine x plus 1 equal to 0, which means if I subtract 1 and divide by 2, cosine of x is equal to negative 1/2, which means I want to know where on my unit circle is cosine equal to 0 and where on my unit circle is cosine equal to negative 1/2. So this is where we have to remember that circle that we just talked about. Cosine is the x coordinate. I want to know when the x coordinate is 0. The x coordinate is 0 when we go straight up and straight down. That's going to be at pi over 2 and 3 pi over 2. So those are two possible answers. We're just going to go from 0 to 2 pi for this one, rather than doing all solutions. Cosine, the x coordinate is going to be negative 1/2 here. Negative 1/2, I remember from my chart or my circle, negative 1/2 is the short distance. Remember, 3 is long, 2 is medium, 1 is short. Negative 1/2 is short, so it's going to be a short distance in the negative direction, giving me this point and this point. If I think about the points on a clock, then I could count 1, 2, 3. That's 4 pi over 3. 4 pi over 3 reduces, 4 pi over 6 reduces to 2 pi over 3. If I want to go all the way around, we've got 1, 2, 3, 4, 5, 6, 7, 8 pi over 6. 8 pi over 6 reduces to 4 pi over 3. And that's going to give us 3 solutions on our unit circle that are going to work for this equation to make the relationship a true relationship. Ella on TikTok is asking, just to make sure, is this only associated with right angles? Well, it depends on what we're doing with those angles. For example, let me erase this. And as I erase this, remind you that we are here answering your trig questions every week at this time. But if you want to make sure you have the schedule of all of our tutoring sessions, make sure you're scanning this QR code up in the corner, because the schedule might change week to week, and there are lots of live sessions available to help you be successful in your classes. Here at Chegg, we want to help you in any way possible to be successful in those courses, so make sure you're checking that out. So typically, when we're dealing with trigonometry, we say it has to have a right angle in it. For example, I might know this is a 40-degree angle, and I might know this side is 5, and I want to know what that side is. On a right angle, if I have a right angle in my triangle, I can say, because across from the 40, we call that the opposite side. Across from the right angle, we call that the hypotenuse side. We have the opposite and the hypotenuse. The trig relationship that uses opposite and hypotenuse is the sine. So I can take the sine of the angle, and that's going to equal 5 over x. That's that SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And then I can solve this resulting equation by multiplying both sides by x and dividing both sides by the sine of 40. That way the x's reduce out and the sine of 40 reduces out. So I end up with x is equal to 5 divided by the sine of 40. And then I can actually figure that out on my calculator. Let's go ahead and do that really quick. 5 divided by the sine of 40. Make sure I'm in degree mode. I get 7.78. So this side here would be 7.78 units long if that's a 40-degree angle and that side is 5. So yes, it has to be a right angle. Unless we use not just sine, but maybe a property of sine, like the law of sines. So the law of sine says if we don't have a right angle, let's say I've got a triangle like this one, no right angle, and it's not to scale, by the way. And let's say this side is 5 and this side is 40 degrees, but there's no right angle this time. Instead, the other angle is maybe 70 degrees. I can still find the side across from the 70, just like I found the side across from the 90, but we have to use what is called the law of sines, not just a regular sine. The law of sines says I can take the sine of any angle and divide it by the side that's across from it. That will always be equal to the sine of another angle, and we divide by the side that's across from it. And so then we can solve this equation. Since it's two equal fractions, we just need to multiply the diagonals, and we end up with 5 sine 70 is equal to x sine 40. Well, to solve for x on this equation, all I have to do is divide both sides by the sine of 40. And x is equal to whatever 5 times the sine of 70 divided by the sine of 40 is. Now, be careful with your calculator, because usually when you type in sine, it opens up a parentheses. So we want to make sure we close the parentheses as well. So let's take a look at what that does for us. We've got 5 sine 70. I'm closing the parentheses, divided by the sine of 40. That tells me the distance is 7.31. So this x distance is 7.31, which makes sense. If this angle went from 90 degrees and we shrunk it down to 70 degrees, we would expect the size to shrink down of this side, 7.7 down to 7.31. So yes, we can use trig with non-right angles. We just have to make sure we're using the formulas correctly, whether it's the law of sines. We also have a law of cosines. If someone wants to see a law of cosines example, stick it in the chat, let me know, and we'll do one. Or maybe you want to see the law of sines, which gives us two triangles with our given information because of the ASS property. Whatever you want to see, put it in the chat. We're going to try and answer your questions today, because this is your live office hour with Chegg. Another thing I want to see in the chat, though, is if you could also take a moment, tell me where you're from. I'm always curious who's logging in. We've had some people log in from Europe on past lives. I want to see who's here from where. Stick it in the chat, and I'd love to give you a shout out. Excellent. We got a couple questions. If one side is 5 and the other side is 7.78, what is the width on TikTok? Do I have an angle? Like, do I know there's a right angle? If I know there's a right angle, we can do that. I need to know one of the angles, though. Or we can make that into a law of cosines problem as well. So let's say if I knew the angle in between them, let's say I knew this was a 65-degree angle. And yeah, let's do the law of cosines. And you said you wanted to see sides of 5 and 7.78. So we've got sides of 5 and 7.78. And we want to know what is the width of that triangle or that distance it covers. We do this a lot to kind of decide how wide apart something is. Like, for example, I want to know how long something is on the other side of a river. So I can take a 65-degree angle to the left side of it and to the right side of it, and then I can see how long that thing is, or that property, or that building, or whatever that might be. We also can use this idea as we're looking up into space, and we're looking up at how stars are moving across space as the planets move around the sun. What's the distance that's been traversed? We use this law of cosines concept to help us make those connections and figure out what's going on. So law of cosines, the idea of the law of cosines is it's based on the Pythagorean theorem that says a squared plus b squared equals c squared. The problem is that relationship only works if we have a right triangle. If we don't have a right triangle, we're going to do a small adjustment to make this work. I want to also do a quick shout out to the Philippines. I think you're our first Philippine person logging in. That at least has told us they're from the Philippines. That's exciting to see you. Welcome. Glad to see you here. Also, if anyone else is logging in, tell me where you're from. I want to give you a shout out as well. As I was saying, the Pythagorean theorem only works with right angles. So if we don't have a right angle, we need some type of correction factor. And the correction factor that we're going to introduce is 2ab times the cosine of the angle between them. So A and B are the two sides of the triangle that are around the angle. So we can say A is 7.78 and B is 5. Capital C is the angle that we have between them. And so I can use these and this law of cosines to find this missing side. A squared is 7.78 squared, plus B squared is 5 squared, minus 2 times A, which is 7.78, times B, which is 5, times the cosine of C. Oops, I actually know what C is. C is the angle 65 degrees. That's going to equal my little c squared, or in our case, the other side, which is our x squared that we're looking for. This big ugly thing, if it has no letters in it, is actually not too bad because we can just stick this in our calculator exactly the way it looks. So let's do that really quickly. I've got 7.78 squared plus 5 squared minus 2 times 7.78 times 5 times the cosine of 65. Put that all on my calculator, I get 52.64. 52.64, but remember that's equal to x squared. So to get rid of the square, we'll take the square root of both sides, which I typed in my calculator wrong. Give me a second. There we go. 7.26. So x then is going to equal 7.26. That is the distance of that opposite side from the 65-degree angle. That's the law of cosines. It's really just the Pythagorean theorem. So a squared plus b squared equals c squared with this little correction factor stuck inside. All right, let's take a look at doing some angle of elevation and depression. These are great application problems where we can see the trigonometry properties actually work out in real life situations. Some of it's just a little bit of knowing the vocabulary so we can set up the picture correctly. So let's say I am looking out a window, and out that window, here's my window. Out my window, I can see to the top of a really tall building. Let's say that angle of elevation, which means the angle made with the horizontal, the angle of elevation is 23 degrees to the top of the building. Then I look down to where the bottom of the building is. When I look down to where the bottom of the building is, that's the angle of depression. Depression meaning down, not sadness. Let's say that goes down another 36 degrees. If I know how far away I am from the building, we should be able to actually figure out how tall that building is that we're looking at. Let's say that we're looking at, let's go 20 feet. Let's say I'm 20 feet away from the building. We're going to break this up into two triangles. First, looking at this top triangle, which I'll color in blue here. Can't really tell it's blue in there, but it's blue, trust me. From the 23-degree angle, this 20 feet is the adjacent side, and I really want to know the height, which is the opposite side of the triangle. So from the 23, opposites across, adjacent is next to. Which trig ratio, go ahead and type in the chat if you remember, which trig ratio is going to use the opposite side and the adjacent side? If it helps to think about SOHCAHTOA. If you said tangent, tangent uses opposite and adjacent. You were right. Tangent of 23-degree angle is going to equal the opposite over the adjacent. I don't know the opposite. We're going to call that x. But we do know the adjacent. That's 20 feet. And we can solve this by multiplying both sides by 20. And x is equal to the 20 times the tangent of 23, which I'll put in my calculator and get let's call it 8.5 feet. Then we say, okay, that's this top part, but we need to still get this bottom part. So the angle of depression looking down at the bottom part is this triangle, which is another right triangle. Again, I know the adjacent side is still 20 feet, and we want to find the opposite side. I'll call that y. So again, we have the opposite and the adjacent. To find that, we're going to use the tangent. So the tangent of the 36-degree angle is the opposite, we call that y, over the adjacent, which we said was 20. Multiplying both sides by 20, and y is equal to whatever 20 times the tangent of 36 is. And so again, I'm going on to my calculator. 20 tangent 36 is about 14.5. So this top part we know is 8.5. The bottom part is 14.5. What do you think we got to do to get the total? We're going to add these numbers together. 15 plus 23. That's a 23-foot tall building. That's how we can use angle of elevation and angle of depression. I want to give a quick shout out to a couple people that are putting in the comments. We've got the one who waits is here from Canada, taking Calculus 2 at the moment. You should come to my Calculus study party that we're going to do tomorrow at, I think, 5:15. I'm not actually sure the time. So scan this QR code in the corner, and we're going to do all things calculus at that time, which will include things like trigonometric substitution, which I know a couple people are asking about, but that's a bit beyond the scope of this live. But come back tomorrow for a live, scan the QR code, get the schedule, and I'd love to have you join our calculus live tomorrow evening. All right. More questions coming up about real life situations. All right, so real life situations, trig is used all the time. The question is, which real life situation do you want to use? One place trig is used is as we're keeping track of the tides of the water. Because let's say you're somewhere, I'm going to make up these numbers, but you can actually look up the actual numbers to predict where the tides are going to be at the beach. Let's say at 8 a.m., the tide is at its highest point. It's high tide at 8 a.m. And let's say that high tide happens at, it's 15 meters tall, 15 meters in. 6 hours later, you're going to get a low tide. So 6 hours later, 8 plus 6 is 14, which is 2 p.m. Is that 6 hours later? Yes, it is. Then you're going to get a low tide. Low tide, let's say that comes down to just 3 meters. we can model where the tide is actually going to be at any point in the day using just this information by applying this trigonometry concept in this real life situation. So here's my graph. And we're going to say at 8 a.m., so that's 8 hours after midnight, we have a high tide here at 15 meters. Let's give it a y coordinate of 15 meters. And then 6 hours later, there's a low tide at 2 p.m. 2 p.m. is 14 hours after midnight. 2 p.m. it is at 3 meters. And so you can see the tide has gone from high down to low. And then it's going to come back up to a high. Then it's going to come back down to a low. And you end up getting this beautiful graph that looks like a sine or a cosine graph. Let's see what the equation is of that graph. The way we get the equation of a graph is first we need to know where the midline is on the graph. So the midline is going to be right in between 15 and 3. If I average 15 and 3, 15 plus 3 is 18. 18 divided by 2 is 9. So that tells me the midline here is at 9. And then we can see how much we're going up and down from 9. We're going up and down a distance of 6. We also need to decide where we want to say our graph starts. And you have the flexibility to choose where you want the graph to start. I'm going to choose the graph to start at this point because that's the first point we know on the graph coming in from the right or from the left. That starting point then has come in a distance of 8. That's a horizontal shift of 8 on this graph. The other thing that's important to note is because we're starting at the top of the graph is going to be a cosine graph. If we start at the bottom, it's a negative cosine. If we start at the midline going up, it's a sine. If we start at the midline going down, it's a negative sine. You can start at any of those points, and it's just going to change how much horizontal shift we have and whether or not we're doing sine, negative sine, cosine, or negative cosine. But in this case, I chose to start at the top. That's a cosine. It's a positive cosine. In front of cosine, we're going to say the amplitude, how tall it's going to get from the midline. In this case, it goes up 6 from the midline. Inside, we're going to take 2 pi and divide by the period, or how long it takes this thing to cycle from top to bottom to top. Notice it took 6 hours to go from the top to the bottom, which means it's probably going to take another 6 hours to get from the bottom to the top, giving us a total of 12 hours in our period. So we'll take 2 pi and divide by 12. Well, that just reduces 2 pi over 6. And then in parentheses, we're going to take x and subtract our horizontal shift, which was 8. And then we're going to add our vertical shift of the midline. The midline normally for a cosine graph is right in the center. We move that midline up to 9. So we're going to say plus 9. And now this equation helps us actually model where the tide is going to be at any point in time. So now I can say, gee, I want to know when this tide is going to be 3 feet tall. No. Let me see. 3. I'm making this up on the fly, so I want to make sure it works. 3, 12? Yeah, I want to know when the tide is 12 feet high. Okay, we can figure out when the tide is 12 feet high by solving this equation for x. First, I have to subtract 9 from both sides. When I subtract 9 from both sides, I get 3 equals 6 cosine of pi over 6 times x minus 8. Then we can divide both sides by 6. Dividing by 6 is going to give us 1/2 equals the cosine of pi over 6 times x minus 8. And then we're going back to our unit circle. Notice how this all connects to this very simple application problem. In the unit circle, when does the cosine, the x-coordinate, equal to 1/2? Remember, 1/2 is a short distance. We have the long distance of root 3, medium distance of root 2, and a short distance of 1. over 2. So we're going to do a short x distance of 1 over 2. That's going to happen here at the top and here at the bottom at either pi over 3 or what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi, which reduces to 5 pi over 3. Either pi over 3 and 5 pi over 3. So the first time is going to give us, first time it hits 12 meters high. And then the second answer, the 5 pi over 3, will give us the second time that it's over 12 meters high. Maybe we want to know how long it stayed above 12 meters. So we need to find both of those answers. Let's see, I'm running out of whiteboard space. I'm going to go off screen. I'm still here. Trust me, I'm still here. I'm just left-handed. So we're going to say that this inside stuff, the pi over 6 times x minus 8, is equal to both pi over 3 and pi over 6. And then we're going to solve that resulting equation by first multiplying by this reciprocal of 6 over pi, 6 over pi, 6 over pi. When we do, we get x minus 8 is equal to 6 over 3 is 2, and 6 over 6 is 1. And then I can add 8 to all 3 parts. And we find out x is equal to 10 and 9. Wait a minute. Did somebody notice I copied that wrong? We said our second answer was 5 pi over 3, and I wrote pi over 6. Back up. The second answer we said was 5 pi over 3. So when we multiply that by 6 over pi, pi's reduce out. 6 over 3 is 2. 2 times 5 is 10. So x minus 8 is equal to 2 and 10. So if I add 8 to both sides, we get 10 and 18. So what we actually ended up finding, because of our shift, we actually ended up finding these 2 points here and here. 10 hours, and at 18 hours, it is hitting 12 meters high. Well, if I want to see how long it's there, we see it's there for 8 hours. 8 hours, it's below. It's a 12-hour cycle. So for 8 hours, it's below, and 4 hours, it's above. So that's a great example of how trigonometry can help us in real life. Notice there we needed the graph. We needed to know how to solve. We needed to know the unit circle. And then we just need to be able to interpret that result that for 8 hours, the tide is going to be below 12 meters. And for 4 hours, the tide is going to be above 12 meters. Great question. Thank you for bringing that in. There were a couple comments that came in. I'm sorry, where did the 2 pi come from and why is it pi now? Where did I write 2 pi? Oh, right here. You're probably asking about this right here. Great question. Let's dive into that a little bit deeper. So normally we say the equation of either a sine or a cosine graph, it can be sine or cosine, is a times either sine or cosine times 2 pi divided by the period times x minus the horizontal shift plus the vertical shift. So again, A is the amplitude. This is how far we went up and down from the midline. So on our graph, we went 6 up from the midline and 6 down from the midline. P is the period. And I think this is what you're asking about specifically. 2 pi is a full circle. So normally, when we're dealing with sine and cosine, 2 pi gets us all the way around the unit circle. However, we're going to divide that by the period of the application problem we're actually looking at. With tides, a period ends up being 12 hours. You get a short and a long twice a day. If we're talking about temperatures over the year, the period is going to be 365 days. If we're talking about going around a circle, maybe you're on a Ferris wheel or maybe you're looking at a wheel that's turning or something, the period might be something like 20 minutes on a Ferris wheel. It might be just a couple seconds on your bike, whatever that might be. The period is how long it takes to get around. So in our case, the period was 12 hours. So I had 2 pi divided by 12 hours. And so the reason why it reduced down to pi is I just divided them both by 2, reducing 2 pi over 12 down to 1 pi over 6. So that's the period. H then, as I said, is the horizontal shift. That's the horizontal shift to either the sine or cosine starting point. That also determines if it's sine, if it's cosine, if it's negative, if it's positive. That comes from there. K then is the vertical shift. Could somebody please explain to me, because I don't know why, H horizontal shift, that makes sense to me. K, why is K the vertical shift? But we always use K as the vertical shift, no matter what. So that's whether it's sine or cosine, or it might be a parabola or a hyperbola or an ellipse or even a circle. We always use K for the vertical shift. That's just what it is. So that's kind of the formula we use whenever we're making the equation of a graph. Excellent. Great questions coming in. Thank you for asking that one about the period, specifically what was going on with the period. All right. Great question came in from Instagram. Yasamelakatie67 wants to know advice for a beginner to be a mathematician. Great question. And while I'm answering that, we've probably got time for about one more trig question. So stick your trig questions in the comment. Do you want to see more proofs? Do you want to see another graph? Do you want to see more unit circle? Tell me what you want to see. Maybe we'll end with a proof, but let's see if there's something else that comes in the comment. What do you need to know, though? What do you need to do to become a mathematician? Really, to be a math person, it only takes 2 things to be a math person. I'm going to let you in on the secrets. Some of you say, I'm not a math person, I can't do it. I'm going to let you in on the secret. It only takes 2 things. And you can do both of these things. The first thing, you have to be a person. The second thing is you have to do math. All you have to be a math person, just a person who's doing math. So which means when someone says they're not a math person, they're just not doing math in the current moment. And you can be a math person if you just take the time to do math. What does it mean to do math? It's solving problems, finding patterns that we can apply to different situations. The sine graph, for example, that we were looking at, it can apply to tides. It can apply to temperatures. It can apply to where a circle is as it moves around. It can apply to so many great things. We can talk about light photons moving in a wave, except they don't move in a wave, but they do, which is weird, but I'll save that for the physicists to explain. But to be a mathematician, you just have to embrace problems and challenges and not be afraid to stew in the discomfort. Learn, challenge yourself to grow in some unexpected ways. Do hard things, do hard problems. And one of the hard problems that come up a lot in trigonometry are proofs. Proofs can feel almost tricky. So let's see if we can do a proof problem. Let's see, I want to do one that's not like one we've done so far. Let's try, oh, so many of these are similar. I want to pick something very different. Let's do 1 plus tangent over 1 plus cotangent. If you do that, you get secant over cosecant. Whoops, cosecant. There we go. Let's see if we can prove that as we wrap up our trig exercise for the day. Now with proofs, we said we like to work on just one side. It doesn't matter which side. So I'm going to pick the more complicated looking side, and then we're going to try and simplify it as much as we can. The left side is clearly more complicated. There's a lot more going on there. If I have no idea what I can do with that, which I really don't have any idea what we can do with this, let's rewrite everything as sines and cosines. So for example, tangent is sine of theta over cosine of theta. And cotangent is cosine of theta over sine of theta. Now, when you do that, when you write everything as sines and cosines, it will almost always happen that you end up with little fractions inside of a larger fraction. When we have little fractions inside of a larger fraction, our strategy from there is to go through and multiply by the common denominator. The common denominator here is we've got a cosine and we've got a sine. So I'm going to multiply by cosine sine on top and bottom. Now, as we do that, it's going to distribute onto both parts. So I'm just going to go ahead and show that, multiplying by cosine sine here, cosine sine. And then it's nice because the cosines reduce out and the sines reduce out. So I'm left with cosine sine plus sine times sine is sine squared over cosine sine plus cosine times cosine is cosine squared. There might be a desire, a temptation, don't give in to this, to reduce out the cosine sine, because it's the same thing on top and bottom, right? Wrong. You cannot do that. The reason is because of this plus. We can only reduce if you have factors, not terms. Factors are multiplied. Terms are added. You cannot reduce things that are added and subtracted. So if we can't reduce terms, let's see if we can get factors. The reason you spend all that time factoring in algebra is because factors behave so much better. We can do things with factors that are multiplied together. So let's factor this. On the top, there's a common factor of sine. So I will factor out a sine, leaves behind a cosine plus sine. On the bottom, the common factor is cosine. So we're going to factor out the cosine, leaves behind sine plus cosine. Now, addition is commutative. You can switch the order. Cosine plus sine is the same as sine plus cosine. And because this factor is multiplied, now I'm allowed to actually go in there and reduce out the cosine plus sine with the cosine plus sine. That's going to give us sine over cosine. But we want secant over cosecant. That's not what we want, but it's really close. Sine is related to cosecant because it's the reciprocal. So I could rewrite the sine as 1 over cosecant. And the sine is over the cosine, which is the reciprocal of the secant. I could write that as 1 over the secant. Well, when I'm dividing with two fractions, we can multiply by the reciprocal. So 1 over cosecant can be multiplied by the reciprocal, which is secant over 1. And you can already see where that's going because that's going to give us secant over cosecant, which is what we wanted at the very beginning. And that will complete our proof. So our general proof strategy, really, we're just looking for anything that we can do to simplify one side. Often that means we're going to write everything with sines and cosines and then multiply to clear out the little fractions. Be careful not to reduce terms, though. You have to factor before you do any reducing. All right. Great questions have been coming up and coming in. I really appreciate all your activity and questions. One person asked about proof by induction. We are going to do an algebra study session in 30 minutes. We're going to take a 30-minute break here. And then in 30 minutes, we're going to do an algebra study session. I will start with the proof by induction. So come back. Several people were asking, come back in half an hour to Cheg's channel, and we'll do a proof by induction together on the algebra review session. Up here in the corner, you can scan to get the schedule of all of our lives. There is lots of great things happening. Also, don't forget, you might have seen in the chat, Cheg is doing a special promotional right now. If you sign up with them, they will give you a discount on your first month. I think the discount code is in the chat somewhere. Where did I lose the discount code? Well, it's in there. They'll probably stick it back in there for you. But it's been great for you to join us. Your engagement has been so much fun. I hope I made trigonometry a little more enjoyable and helped you feel a little more confident in your trigonometry class today. There's the comment, Cheg Live 50 for 50% off your first month. Thank you. We're here to support you all semester 24/7 to support in your toughest subjects. And so make sure you are following Cheg here on TikTok, on YouTube, on Instagram, on Twitch, for more great learning content like this. Remember, we are here every week, so I look forward to seeing you all next week. Happy studying. Best of luck to you. Thanks for joining us, and I hope to see you.